Hi folks, see you speaking again. Today we're going to emphasize the relationship between counters, decoders, and digits. Let's start it. I'm going to put the power on. Don't worry about the numbers you see here when the power goes on, because unless you have particular means to make a automatic reset when power on, then we can push a button, a manual reset, so the display goes to 0. Interesting thing about the project of today is that at this moment we only have two counters, one for each lower importance digit, like they call it the least significant, and another counter over here for the most significant digit. So only two counters. However, there are only two counters, but you have 1, 2, 3 pairs of displays. And all the three of them, they are working under the control of one counter on each digit. This is because of the famous fan out. We're able from the output of one counter, actually from the 4 outputs of the counter, to give signals to from each output to 3 distinctive decoders commanding the displays. And I could possibly do even more than that, but I just want to emphasize the idea. Okay? Now, the counters are made to work counting either up or down. Like if I'm doing this, the 3 pairs of displays, they advance in the same way. It doesn't matter the speed I'm counting. Or if I'm counting down, obviously, they're going to go opposite way. And as soon as I reach 0, if I press the button again, they go back to 99. Why is this? Because now going back below 0, 99, 98, and so on, the counters are working in BCD code. Remember what BCD code is? All the decimal numbers 0, 1, 2, 3 up to 9, they are coded in binary, but the counter has an internal diagram preventing it from counting bigger than 9. This is why we need 2 digits, because one counter then transfers the signal to the second counter. They are cascaded. Now, let's go a bit further. For a project you use on or you build on a breadboard, because this is a breadboard containing the double size, if I'm considering this one over here, the single size breadboard, they may be 830 or 840 points where you can put wiring, even if you won't be able to use all of them, because they also count the ones for the power supply, and you obviously won't use all. But this is how the breadboards are classified: 830 or 840 holes per section. And the standard breadboard I'm recommending everybody to start with is the one with 2 sections. And my point for today is to emphasize the fact that on a 2-section breadboard, you can put a lot of stuff. However, you have to be a bit creative in order to be able to do so. Because, for instance, this big display here, I have a separate digit you can take a look at. This one, not only it doesn't fit on a single section, it does not even fit on a double section like this one, because as soon as you try to plug it over here, there is no room around it, having pins up and down. There is no room around it to place any wire to make the link to the rest. And imagine if you put 2 of them are going to take the whole board, so the board becomes useless for any other circuits. So for that reason, it's much better to have the big displays out of the breadboard. And for that, I have here a little trick, a connector making the link to the display. And this is using an adapter, and we discussed about this kind of adapter and about the cable. Just give me a second to show it to you. If I'm going over here and I'm showing you, I'm going to put the links in the description of the video. There was a video I published about make your own flat cable in minutes, how to crimp IDC connectors, because this one here is an IDC connector. And particularly about this one is an adapter from the IDC connector to the breadboard, and it's over here. Do it yourself, 16-pin or 20-pin IDC to breadboard adapter. Okay, I'm gonna put the links so you're gonna be able to watch them again. And this is the reason we had these projects before, because the purpose was how to extend the functionality of such a breadboard without having all the components plugged on it. You need adapters. Now, if you want to build a counter, remember, you cannot only use a counter, you have to have the counter. Then you, in order to be able to use the digit, you need a decoder and then the digit itself. So you need three bodies in order to make it working. The counter over here, the decoder, and then the digit. So on the other side is the same. The counter over here, the decoder, and the digit. Okay? So you need these three. And there are different ways to build that assembly between the three. And if I have here the counter, I send the signal to this assembly right over here. This is a hybrid board because the decoders are here, one for each of the two digits. And here are the network resistors because you need on some decoders to put resistors limiting consumption of the LEDs making the display. So when you need resistors, then you are going to mount them between the decoders and the digits. And my reason I have to use the network resistors is that right now the voltage this project is working on is 5 volts. And not because I won't be able to make it working at 12 volts for the counter, but because we're going to find it later for that particular display over here, which is only working at 5 volts. Okay? So for this big display, when I need it to work at 12 volts for other projects, I have decoders working at 12 volts. They are the CMOS decoders 4543. And I'm going to only change the sizes of these resistors. For 5 volts, I'm using 220 ohms. And I'm going to remove it for one for each of the decoders. And I'm going to replace them by 820 ohms. So then I'm going to work very fine on 12 volts. Why do I have to change these network resistors here? Simply because the decoder 4543 was initially designed to power LCD displays. So the consumption per output was limited to 10 milliamps. So I have to take care and to limit the consumption for each of these segments over here to no more than 10 milliamps. This is why we have to change the network resistors depending on what voltage you are operating with, okay? But this, I said this is a hybrid board because I send the signal from the counter through the cable to the decoders. So I need, for each of the digits, I only need 4 wires to come, excepting for the 2 of the power supply. 4 wires to come because the outputs, the 4 outputs of the counter, they become the inputs of the decoder over here, okay? So I need in total 4 wires for one decoder, 4 wires for the other one, and 2 for the power supply. I need in total 10 wires. So this is why I can use this external board, because I connect here an adapter, this one, making possible the connection of an external display to the counter. Now the most, let's say, breadboard friendly displays are the ones having the pins in the top and in the bottom, like these ones over here. So it doesn't matter how big the display you want to make, 2 digits or 3 or even 4, you can place them one adjacent to another and so on. And then they're going to stay very close to each other, minimizing the room you use on the breadboard. And these ones can be found anytime in both configurations, common anode or common cathode. So depending on these, you are going to choose the appropriate decoder. And if you use the decoder I use all the time, the 4543. This one can be used for both kind of configurations by only switching one wire, what we discussed in another video. So the assembly now is working fine with these two, which are very close to each other. Now, some other displays are not prepared to be used, not because they are not prepared, I'm very sorry, it's because they are not so breadboard friendly when they were designed. Like these ones, I mounted over here just for you to see. So in normal conditions, these two ones, and by the way, be careful about their names, because if made by Texas Instruments, this one is going to be called TIL 311, and this is going to be called TIL 312, and they are very different from each other. This one over here is that one. It's exactly like this one. It's a just standard 7-segment display. The advantage is you can find a version with 2 decimal points, which may be very good for some projects. This one over here is the 311, and this is a smart display. They were calling it back in time an intelligent display, because the display is able to show not only the decimal numbers 0, 1, 2, 3 up to 10, but also the hexadecimal numbers, so the letters A, B, C, D, E, F. And the whole decoder is over here in this little square, and above it is the display itself. So you only need to command the inputs of the decoder and the display, the decoder are in the same body, and they're doing the same job as the whole board I have over here, obviously at another size, because this is the size of the display itself is 0.3 inches, and this is 2.3 inches, so a huge difference. But in terms of intelligence, this one is much better. Now, another point I want to make. At this moment, if I'm keeping counting, doesn't matter the direction, okay? All the 3 pairs of displays, they work the same. All of them are showing the decimal numbers. Why is this? Because the counter I placed over here is a BCD counter. So at this moment, it doesn't matter what kind of decoders you have. You may have very different decoders. Here I have a very rare decoder, which is 14495. It's very difficult, close to impossible to find it on the market today. But for those of you who can still put your hands on some, I have here the pin assignment, the pinout of this particular decoder. I'm going to put it on Google Drive if you ever need it. And I'm going to show you soon why do I use it over here. But the decoder on the other side, this one, is a 4543, exactly like the ones I'm using on the big display. And this one, I said, the decoder is already incorporated inside the digit together with the display itself. So as long as the counter is only a BCD1, it simply won't matter. Here I have 14495. Here I have a actually 7448 for a common cathode. Here I have the decoders embedded inside. So you can also use the 4543 like here. So different decoders. You simply won't be able to see the difference. But what if I put the power off for a second, I remove that counter from here, that BCD counter. You see, that BCD counter. I put it aside, and I put a standard binary counter, which is counting hexadecimal. Then, if I do this, and I put the power back on, you're going to be able to really see what difference does it make. It shows a 0. But in the moment I start to count, let's say I count up. I go to 9, and as soon as I go over 9, take a look how different these displays are. This one here doesn't show anything anymore. Why? Because as soon as you go over 9 in binary code, which is now 10, this is 1010, the decoders 4543 won't be able to recognize these binary codes. Why? Because they only recognize the codes coming up to 9, BCD code. As long as the codes coming to the decoders are bigger than 9, 10, 11, 12, 13, 14, and 15, you won't see anything on the display, it remains blank. But on these ones, you're going to be able to see something. This is the equivalent for the 10, as you see it on only one display. If I continue to count, then here, that intelligent display is going to have a very complicated decoder inside, and is showing with capital letters all the codes A, B, C, D, E, and F. As this one here, the decoder associated to it, this one, is able to display A, B, C, D, E, F, but some of the letters, they appear as lowercase, like here it simulates the B lowercase. As I'm continuing to count, this one still doesn't show anything because again the codes are bigger than 9. This is showing the letter C, as this one does. When you go for D, this one, the intelligent display, has the complex decoder here inside, and it's able to show on uppercase all the letters up to F. This one shows the D lowercase because it's impossible on a 7 segment to show otherwise. Okay? If you continue to count, the next is E, which is the same for both, and the last is F, which is the same for both. But again, this is only because here I have a decoder understanding hexadecimal playing on a 7 segment display with uppercase and lowercase, and this is an intelligent display. The decoder is more complicated. It is able to display uppercase for each of the letters of the alphabet because the display itself is derived from a dot matrix display. So the display itself is a bit more complicated. Okay? As this one didn't show anything. But as soon as after F you press it one more time, you reach back 0. So then you're going to see something. And of course, because it's a 2-digit counter, the most significant digit, the one on the left, was incremented to 1. So up to 9, you won't be able to see any difference. But as soon as you go over 9, it's going to be the same problem. Okay? So let's go backwards. So as we were counting backwards, and if we press one more time, now going backwards on the least significant digit, of course, we go to F, which is 15, and it should be then 14, 13, 12, 11, 10, 9, and so on. Now, why am I messing up with these displays? First is because I want you to see to make the distinction between using a pure binary counter, which is a hexadecimal, counting 0 to 15, only on 4 digits, on 4 bits, sorry, on 4 outputs, and a BCD counter, which is only counting 0 to 9. So if I'm stopping the power and I'm replacing this one by one of my very old counters. This one here is an extremely old one. You can see it better on the screen. This one here, because I made a list of these counters for you just to see how big is the variety of these counters you can find on the market today. With the exception of this one here, which is extremely old. This was the military version back in time, in the 70s. You can still find this kind of very good counters on the market in different flavors. Here on the left is the version only for the BCD counting, and it's called 192. Here on the right is the pure binary or the hexadecimal counter, which is counting 0 to 15, which is 193. The numbers are very easy to memorize because they are consecutive, okay? What is amazing about the variety of this package, regardless the technology in use, TTL up to here, this is a very good version because it's advanced LS, or CMOS in 1, 2, 3 distinctive versions. So it exists in all the 3 versions. All these, unlike a lot of other packages, these ones, they have the same pinout. So you want BCD, you put anything ending with 192. And I put this one here in orange. This is my favorite. This is one I'm using right now. And here is the hexadecimal one with the 193, and this is the one I'm using right now. But you can use any of the others I checked, and all the others, they can still be found on the market. And I wanted you to see that even using the very old one, which is not in manufacturing for many years already, I just have a couple of them for my demos, but other than that, I almost never use them. But if I'm mounting this one here, even this one, which is a very old TTL one, it should work just fine. So power on, regardless what you see first. Then, if you start counting, it's going to count like all the others. So it doesn't matter, it's very old. The diagram is still the same. And is the proof that the newer ones, including the CMOS one 40, 192, or 193, they successfully replace the old ones that cannot be found anymore on the market. I'm gonna stop the power one last time. I'm going to replace the old one by the BCD to restore the counting in decimal. Okay, power on, reset, count up, count down. When you go back to 0, it goes 99. You won't see the letters A, B, C, D, E, F. So normally in standard projects, that's what you need to do. Only to count 0, 9 or 0, 0 to 99. And we're going to see that there are other projects when you may need the binary or the hexadecimal. Now my last point for today is about this particular display made of intelligent, let's call it intelligent display. Okay? Normally, if you plug such a package on a breadboard, it's going to stay like this horizontally, simply because the pins are not placed top and bottom like on these ones here, but they are placed on the two lateral sides. Okay? So this way, because you have to put it along the slot, you have no other choice but placing it like that. And the other one, which is a simple 7-segment display, has a similar pin out, so you cannot place it otherwise. But if for some projects you need the digits to show nicer, like this one here, you need to build an adapter. And this is going to be the subject for the next project. How to build such an adapter to make one of these, especially the intelligent one. By the way, it can still be found on the market, especially on eBay. I was tempted to make a new order. I'm still thinking about it. But since I have already a dozen of it, I'm not ordering them soon. How can you make these ones showing exactly like the breadboard friendly, showing like that? So you have to make an adapter like this. And if you do it, instead of having them aligned this way, they're gonna be aligned properly, exactly like this one. So that being said, I hope I tried to make it clear for today about the relationship between counters, decoders, and digits. So let's meet the next time to make the adapter for the intelligent displays. Thank you very much. Bye-bye.